For the last lecture of this class, I'm going to introduce water remote sensing. And firstly, some concepts on water remote sensing. Then I'm going to introduce the spectral response of water. And the water here refers to water bodies, okay? And you will know that the response of water bodies is not only about pure water, okay? It's actually the sum of pure water and other constituents, okay? And then water temperature retrieval, that's a very important application of water remote sensing. And also I'm going to introduce the remote sensing of precipitation and snow, because precipitation and snow, they are different forms of water. It's not water on the ground, it's water for precipitation. It could be water in the atmosphere because cloud is also a part of precipitation. You can consider that. And also snow. Snow is on the ground, but snow actually also includes what? Glacier, ice and snow, okay? So why we care about water? Because water is the origin of life. Water is the reason why this planet is blue. Okay, 70%, 74% of the Earth's surface is covered by water, and 97% of the Earth's volume of water is in the saline oceans. So water remote sensing on oceans is very important. Is very important. And 2.2% in the permanent ice cap. Only 0.02% is in freshwater streams, rivers, lakes, and reservoirs. And underground aquifers, 0.6% of remaining water. And in the atmosphere, in the form of water vapor, 0.001%. So fresh water is actually a very small part of water around the world, but it is closer to our life because we cannot drink saline water. Vegetation, animals, they cannot use saline water to survive. And we care about water not only because we need water to survive, it's also a very important part of our environment, important part of ecology. So why do we use remote sensing to address water issues or water bodies? Of course, traditionally, we can use in-situ measurements to address water pollution, to do water monitoring. Okay, but the problem is that when you send people to do in-situ measurement, it's not possible to cover the continuous space of water body. For example, say the water of a huge lake is polluted by surrounding industry, okay, human industry, and you send people to the lake to do in-situ measurement. Of course, you can do that, but what they can do is carrying out measurements at different locations or at different points. You cannot use something like an image to cover the whole area of the lake, right? So not enough point observations to obtain regional spatial information. Another problem is that you cannot send people to the same location for point in-situ measurements every day. I mean, if there is some accident or event, for example, oil spill or oil leakage in the ocean, of course, for that specific area, you can send people every day there for maybe a month or two to do the in-situ measurements. But that's very special. Usually, you cannot send people to a lake to do measurements every day. Usually, if the water body is very important, maybe the local environment agency, protection agency, they send people to the water body every month or every season or even every year to do the regular measurements. But it's not possible to do temporarily continuous measurements, but satellites can do that because they're flying the sky. They have specific revisit period, and they can observe the same area every several days. And for geostationary satellites, they are looking at a specific area on the ground continuously. They don't have revisit time, right? So they can actually observe the same area or water bodies continuously. So the process of water remote sensing, the core of this is transmittance of EMR above and inside the water. Okay, so here is a figure showing you that the most important part, not the most important, one of the most important part about this figure is this equation. LT is the signal, is the energy you receive, the remote sensing system receives, and it is a sum of LP, LS, LV, and LB. They are atmospheric path radiance, free surface layer radiance of water, subsurface volumetric reflectance of water, and bottom reflectance. We can say that LP is something we do not want in water remote sensing because it has nothing to do with the water body itself. I mean, if you care about cloud or the water in the atmosphere, it might be useful, but in most scenarios, LP is something we do not want because it's about atmosphere, it's not about water. And if you care about the surface of water, LS is something you're interested in. If you care about the water body itself, then LV is something you want. And some people, they care about the bottom of a water body, okay, for reasons. Then LB is something you want. So you can see that depending on the specific application you are carrying out, different components of this equation are important to you, and the rest of them is not important to you. And you need to eliminate them from this equation, from LT, to make sure that the information you have is the information you need. Okay, and what is making this process more complex is that there are optical shallow and optical deep water. So in our daily life, when we're talking about shallow or deep water, it refers to the actual depth of the water body, right? So if there is a small pond, it's only 10 feet deep, then usually we say it's shallow. And on the other hand, when we're talking about, say, Lake Michigan or other huge lakes, it could be several hundreds feet deep or even 1 kilometer deep water body. Then we say they're deep, they're physically deep, but optical shallow and deep, that's another thing. For example, that pond is only 10 feet deep. But if the water is very turbid in that pond and EMR cannot penetrate because of the turbidity of the water, then we say it's an optical deep water. On the other hand, even it's in the center of an ocean, if the water of that ocean is very clean and EMR can easily penetrate it for a specific distance, then we say, compared to that small pond, this ocean water is actually optical shallow water, okay? And there is also a category of inland water, and there is also a category of ocean water, okay? So actually, when you're trying to address the EMR transmission in water bodies, you have to be very careful. You have to find out if the water body you are interested in is optical shallow or optical deep. Is it inland water or ocean water? There is no universal model for the transmittance or transmission of EMR in water. People developed, and they're still trying to develop more models radiation transmittance models to address the transmittance of EMR in different types of water bodies. Okay, so water remote sensing can be very complex, Okay, the goal of most aquatic remote sensing is to extract the radiance of interest from all the other radiance components. Remember this equation here. Okay, usually you are only interested in one or some of these components of this equation. You need to get rid of the rest. Okay, and in water, there are organic and inorganic constituents. Okay, and the bottom characteristics of water bodies, they are different. They are different. So you have to consider all these factors, different types of water body and different constituents in water to actually carry out proper water remote sensing. And now I want to show you the spectral response of pure water first, because we're going to talk about spectral response of water bodies. Okay? So on the left side, we have this figure with two curves. The U curve here is for the absorption of water from 240, which is ultraviolet, to 800, which is near infrared. Okay, so you can see that within ultraviolet, the absorption of water is very strong. And as the wavelength increases, this absorption effect decreases very fast. And in violet, dark blue, light blue, and green area, you can see that absorption of water is weak, is the weakest within this range actually. And after that, it begins to increase again in green area, and you can see that when the wavelength increases and it arrives at yellow, orange, and even red, or no need to say infrared, the absorption of water is strong again. That's the reason why water is usually, especially clean water, looks blue in the nature, right? And when you are looking at the water body in near infrared band, it is sometimes it's purely dark, it's purely black. That's because the pure water absorbs most energy within infrared range. On the other hand, the scattering of the water of pure water is relatively straightforward. It is at its strongest in ultraviolet and decreases as the wavelength increases. Okay, and again, you can see that within blue band and the green band, the scattering of the water is also very weak. So within this band, blue and green, water does not barely absorb, and barely scattering. So it means that most EMR within blue and green band is reflected by water. Okay, and in order to monitor water surface extent, the best wavelength region for discriminating land from pure water is near infrared and mid infrared, because the is very strong there, and you can see the very clear, very crispy boundary between land and water body. Water body is very dark, sometimes just black. Okay, so here is an example. Let's check the third picture here. So here is the island. It's in gray. It's Cozumel Island. It's from Mexico. And the dark area here is Caribbean Sea. So the third figure here is spot band 3, which is near infrared. So from this picture, you can see that the ocean is purely black. You can see nothing because the absorption here is simply too strong. And the middle picture here is for band 2. It's red band. So the absorption effect here for water is not as strong as water in near infrared band. So you can see here, except this island here, the color changed, but you can see that we can see some sediment along the boundary, along the beach, and you cannot see these sediments in this picture because in red band absorption of water is weaker compared to infrared. And if we do this again, we decrease the wavelength here. So in green band, we can see this very clear reef at the bottom of the ocean. It means that compared to near infrared, even compared to red, in green band, the absorption of water is even weaker. That's the reason why we can even see the bottom of the ocean when it is not that deep and when the ocean is very clean. Okay, so if let's get back. If you care about the boundary between land and water, you want to discriminate them. Of course, you want to use near infrared band because you can see that the boundary here is very clean. Water absorbs most energy. But if you use red band or even green band, the boundary is not as good as the boundary appeared in near infrared band. So if you care about the surface of water, you want to find out the boundary, land-water boundary, then near infrared or mid infrared. Okay. And then let's talk about constituents in water. Like I said, water bodies, they are very complex. It's not only pure water. There are inorganic suspended minerals or SM. They are the reason of turbidity of the water. They are the most important factor um, affects the turbidity of water. Organic chlorophyll A because there is vegetation, also vegetation in water, and also there is something called color dissolved organic material. We call it DOM, or sometimes we call it CDOM because it's color, and its color specifically is actually yellow. So sometimes we call it yellow matter, or we call it DOM, or we call it CDOM. They are the same thing. And the total amount of absorption and scattering, attenuation that takes place in the water column due to each of those constituents. Okay, so it is useful to look at the effect that each of these constituents has on the spectral reflectance characteristics of a water column. So if you're actually looking at a specific water body and you're interested in the electromagnetic characteristics of this water body, reflectance, absorption, and scattering, you actually have to be careful with all of these constituents of water body instead of pure water. Okay. And for inorganic constituents, minerals, they are basically minerals. Okay, minerals such as silicon, aluminum, and iron oxides, they are found in suspension in most nature water bodies with different concentrations, of course. So the particles, they have different size. And the sediment comes from a variety of sources. What's the origin of their of these particles, including agriculture, erosion, right? Weathering of mountainous terrain. This is nature, right? Short erosion are caused by waves or boat traffic. So this could be human activity, could be nature. And volcanic eruptions. This is pure nature. So most suspended mineral sediment is concentrated in the inland and nearshore water bodies, and they are carried out into the ocean by water. For example, by rivers. At river mouth, you will see a lot of sediment, and also by human activity, say human transportation, and human life, human industry. So the sediment in rivers and in oceans, they're from different sources and carried by different processes. So here is an example, space shuttle photograph of the suspended sediment plume. So we can say this plume area at the mouth of Mississippi River near New Orleans, Louisiana. So the dark area here is ocean, and we can say here is generally the boundary. It's hard to tell between land and ocean. We can say here we have different branches. They are actually indicating that the different streams of Mississippi River and different water currents, they are carrying sediments into the ocean and form this huge plume of sediment. Okay, it's a gray white area, right? And of course, it's not clean. The water is not clean. It's full of minerals. Okay? And we can say we have small white polygons here, right, at the bottom of this figure, and each one has a shadow in the ocean, right? What are they? They're clouds. They're clouds. Okay. And here is another very simple tool to address the concentration of inorganic constituents in water. It's called Secchi disk. It's a circular plate that is lowered into the water until it cannot be seen. So you can see this is a disk. It is attached to a rope. So you can hold the rope and put the disk into the water and let go the rope. So the disk will just dive into the water. And when you can barely see the disk, you stop the rope and measure the depth of the disk right now. And if it is very deep, it means that the water is very clean. The inorganic constituents concentration is very low, which means the water is very clean, the turbidity is very low. Right? If the depth, the Secchi depth is very shallow, which means that maybe after say 20 centimeters, you cannot see the disk anymore. It means that the water is very turbid. Okay, so the Secchi depth is inversely correlated with the amount of suspended material in the water. But you can see that here, the Secchi depth is an indirect indicator of the turbidity of the water because it's not the concentration of inorganic constituents. It's just the depth. But it's very convenient. It's easy to make. This tool is easy to make. It's easy to use, but it's not that accurate. We only know a depth instead of the actual concentration of inorganic constituents. Okay, I will just stop here and continue in next video. Thank you.